So welcome you all to this physics colloquium. Today we have with us, it's a distinct pleasure to have with us Professor Pieter Kok. He is a professor of theoretical physics at the University of Sheffield, and is one of the leaders in theory of quantum and applied quantum information. Specifically of optical quantum information technology. So he has a PhD degree from University of Utrecht, and then did his PhD in physics from University of Wales. Later on, he was a research fellow at NASA at HP Labs. Later on, a research fellow at the University of Oxford. And currently, since 2007, he's at Sheffield and currently is a professor of theoretical physics there at the University of Sheffield. So he has a couple of some excellent books to his name: a first course in quantum mechanics, and an optical quantum information, another book on practical aspects of optical quantum information. So really nice books, and I would really recommend them. So today he would talk about quantum imaging. It's one of his main areas of interest is quantum metrology, apart from linear optical quantum computing and hybrid computing system like which involve light matter interaction. So without further ado, let's welcome Professor Pieter Kok, and let's hear what he has to say about quantum imaging and what kind of interesting things lie there. So yeah, to you, Pieter. Yeah.
Thank you so much for this invitation. It's a great honor, and it's great to see you again. I mean, we've met in Sheffield, and thank you also for your kind words about the books. I'm really, as an author, it's always it's always really satisfying to hear people getting something from something that you put a lot of work in. So yeah, now I put only my name on this front slide here, but there will be many people who have contributed to this work. So I will mention them as we continue. And also at the bottom here, there's a logo salad of the various funding bodies that have been kind enough to support this work. So without further ado, let me have a quick look at the structure of this talk. So I want to spend quite a bit on the fundamentals of quantum metrology, because it's not the sort of thing that is usually taught in an undergraduate physics degree. And there's some really interesting ideas there. So that's kind of all old and well-known stuff to the people in the field, but I think it deserves to be more well-known more widely. And then as the main topic, I'm going to talk about quantum imaging as in the context of a metrology setup. And then there's going to be two aspects to that. There's namely the noise reduction that you get in an image, and also the super resolution that you may be able to achieve in imaging. And then finally, I will offer some conclusions, and hopefully there'll be enough time to answer questions if there are any. I'm not entirely sure. All right. Okay. So there we go. Fundamentals. So we can start with the following situation, namely any measurement, any experiment, where you can very schematically separate into three parts: a preparation part, an evolution part, and a detection part. And then, as any experimentalist knows, there's often a feedback loop involved as well. And that can be modeled with it's sometimes quite complicated mathematically, but it can be done. And but this is essentially the model that I'm going to use for any experiment. And you see that we have a quantum state rho that starts out in it's like rho 0. Then we have the evolution that is based on some set of parameters in your Hamiltonian or what have you. And so that changes the state. And then in your detection system, you're going to get outcomes. And this can be a classical experiment or a quantum experiment. It's very general. Then when we consider the measurement outcomes, even in classical experiments, you can define a probability distribution over them. So for example, if we have an experiment like this, like LIGO, where we have a laser into a Michelson-Morley experiment, if we have no gravitational wave coming in, then the left detector keeps on firing. And then when the gravitational wave changes the path length of one of the arms, then you see that detector 2 starts firing. So if the change in path length is indicated by this quantity theta, then you can see that for different values of theta, we have different probabilities for which detector is firing. Right? And if we then look at a sort of a mathematical model of this, then if you look at the probability distribution of your measurement outcomes, so here I drew a 3-dimensional picture where we have 3 different measurement outcomes. I labeled them red, blue, and green. So any dot in this triangle, in the surface of this triangle, is a probability distribution. And so the probability distribution has to change as you change the value of your quantity in order to be able to say something about the value of that quantity theta. Right? So, the probability distribution has to depend on theta if we are to gain any information in our measurements about the quantity theta that we're interested about. And so we can then build a mathematical model, which I'm going to elaborate on a little bit later. But what do we want? We want to know how often do I need to measure in order to distinguish between, let's say, these 2 probability distributions, P and Q. So you can imagine you put your P and Q quite close. And if you do a finite number of measurements, you can never truly pinpoint your probability distribution. So for a given number of measurements, you will have some region of uncertainty. So that's given by these little ovals around that path labeled by theta. And so the question then becomes, for 2 distributions P and Q that are close together, when do I start to see the difference between them? Right? So we have some distinguishability criterion here. And this was analyzed by Ronald Fisher. I put his picture up, but I had a struggle here because this was not a particularly nice person. So I do want to say this out loud. He was a eugenicist. And so, but nevertheless, I mean, his work in statistics was important. And so the Fisher information is named after him, and it indicates the amount of information about theta that is contained on average in a single measurement. So if we take a measurement, we get a little bit of information about theta if the probability distributions actually do change. And so that information is very important, that quantity, because ultimately it will allow us to say something about the precision with which we can measure theta. And so it's a statistical quantity that tells us about the distinguishability of the probability distributions. And I'll get into detail, but I want to prime you that it's an information measure. That is, and then from this information measure, we would like to get a precision measure. And so we need to link this to, let's say, the variance or the mean square error. And this was done by 2 gentlemen, Rao and Kramer. And so the result, which is called now the Kramer-Rao bound, is that the mean square error in our quantity theta is bounded by the inverse of the Fisher information, which means that the larger the amount of information in your measurements, the smaller your error. So it does exactly what you would intuitively expect. And also, the more times you repeat your measurement, the more information you get. And if the measurements are independent of each other, then the information is additive. So you just add more information. And as a result, your variance, your mean square error, reduces with according to this formula here. And so this is the Kramer-Rao bound. So it's basically, you can make your measurement worse if you have, like, for example, really low quality detectors and you have experimental imperfections that are not fundamental, but so that's why it's a bound and not an equality. But this as a bound means also that you cannot do any better. And it's also very interesting because it tells you that physics itself, nature, stops you from getting from doing anything better. And that is an interesting in its own right when you're studying, you know, information, nature as an information processing device, if you like. All right, so the space of probability distributions is actually highly curved. So I drew it as a triangle, and so you may think like, well, the distance in between 2 points, I could just use Pythagoras and there's my distance. But actually, that's not quite. You can do that, but you don't quite get results that make much sense statistically speaking. And so it turns out that this space is curved like this Escher drawing, and so what we want is a metric in this in this space, this triangle, and the statistical distance provides this metric. And in fact, the metric itself is really the Fisher information, and so you can see that for this ds squared, that in fact this is not a flat space because we divide by p. And so you can see that if one of your probabilities is 0, so you're lying on the edge of the triangle, you see that the distance goes to infinity because it diverges, you divide by 0. And so if we look at this, you can see that if you get to the edge of the drawing here, you see that if all the angels and demons are, like, let's say 1 meter tall, then you can see that space is curved in such a way that angels and demons, basically you can fit an infinite number towards the end. So that also means that if you want to walk that way, you walk towards the end, it'll be infinitely far away. And so and this is a Lobachevsky space for those who are familiar with this. Okay, so this is our metric on our probability space. And we call this the statistical distance because it's not the Euclidean distance between the 2 points P and Q. And then the threshold for distinguishing P and Q is that the number of times that you sample your distribution times the statistical distance squared must be greater than 1. So notice also I moved away from the infinitesimal form for ds squared to delta s squared because I want, with a finite number n, which may be very large, I want to be able to get that across a finite threshold, namely 1. So that's the distinguishability criterion. And now the Fisher information that I talked about earlier is in fact the speed squared that along the curve. And so where you can think of your theta as playing the role of the proper time. So the faster you go through your, through the curve that connects the two probability distributions, the easier it is to distinguish the two. And so because you're getting further apart. So so this is a little sort of like mathematical background, but I'm not going to use a whole lot of this in the rest of the talk, but I will talk about the Fisher information quite a great deal. So hopefully this gives you a bit of an intuition. And so to help with that, let me give you a couple of examples. So we know the expression that even a stopped clock gives the correct time twice a day. And so we can prove mathematically that this is the case because the probability distribution of the measurement, namely the time readout, no longer depends on time because theta here is the time parameter, but my measurement readout is always the same no matter what the time is. And therefore, the ds d theta is 0 because it's actually all the probabilities are constant, and therefore the Fisher information is 0. So there you have it. A stopped clock cannot be used to tell the time accurately. I'm sure you were all very relieved that I finally proved this. But so let's move on to a slightly more interesting example: the gravitational wave detection with classical optics or single photons. You can do. So what are the probabilities for these two detectors to fire? So detector 1 will fire with this probability, and detector 2 will fire with this other probability. You can quickly check that these two probabilities sum up to 1. And if I now calculate the, because we have the probabilities, and my statistical distance was phrased in terms of derivatives with respect to theta of these probabilities, I can just take the derivatives, square them, and do the manipulation that I need, and I find that the Fisher information is in fact equal to 1. That's great. Then the Kramer-Rao bound becomes the delta theta is greater or equal than 1 over n times, where n is the number of individual photons that we send through, times the Fisher information, and we end up with the standard quantum limit, right? That we know from the regular 1 over root n behavior from statistics. So that it all makes sense, right? It all worked out, and even with this really sophisticated mathematical model, we get exactly the answers that we expect. Now we can also do something a little bit more interesting, and we can prepare a quantum state where all the photons go into one arm and none in the other, or in a quantum superposition with that, we send all the photons in the other arm. And so then we end up with this so-called noon state. And if we somehow measure, you notice that I took away the detectors in this picture because it is a very complicated preparation and measurement procedure, but that's not the point right now. The point is that we do get a two probabilities if we measure in the n0 plus 0n or the n0 minus 0n. And so we have two probabilities, they again sum up to 1. We can take their derivatives, and what we find is that the Fisher information is now scaling with n squared. And when we calculate the mean square error, root mean square error in this case, you see we've put all our photons in one basket. And so we don't have an n in front of the I in the denominator there. So all the n has gone into I, but it's turning up in the Fisher information as n squared. So when we take this the square root, we have 1 over n. But that is a quadratic improvement over the standard quantum limit, which was 1 over the square root of n. And this is what's called the Heisenberg limit. So this is this is very difficult to implement in practice, but this is the theoretical maximum of what you can achieve in terms of the precision with a finite number of photons. Okay, and then, so this is all about the classical, the normal Fisher information, which is all about measurement outcomes. And then there is an extension called the quantum Fisher information, and this is about measurement optimality. So classically, we have a preparation, an evolution, and a detection, and the detection gives us our probability distribution of the measurement outcomes, and we can use those probabilities to calculate our Fisher information. Quantum mechanically, there we go, we have a preparation and an evolution, but we stop there. We do not actually look at at a particular measurement. We actually optimize over all possible measurements, because in quantum mechanics, any observable can be, in principle, measured. And so we want to know what is the best possible measurements that you could do. So, for example, if you want to tell the time, you don't want to use the stopped clock. You want to use a running clock, and so the quantum Fisher information would actually not be 0 as it would be for that stopped clock, because the stopped clock actually has a very specific measurement procedure, a broken one, right? And here for the quantum Fisher information, we can say no. If you used the best possible measurement that you can possibly, that nature allows you to use, then you would get this amount of information. And that is called the quantum Fisher information. And it's something really important. Both the normal Fisher information and the quantum Fisher information can be used for classical and quantum experiments. So as long as you have a quantum mechanical model for your system, even if it's a classical system, by all the means, which we'll see later, you can still calculate the quantum Fisher information. You just need a quantum mechanical model for it. So those are the two things. So the Fisher information tells you how much information do I get out of a measurement. The quantum Fisher information tells me how much information is there actually in the state before I make the measurement. Okay, and so if you find this interesting, and I hope you do, my postdoc Yasminder Sidhu and I wrote a review on this, and it's published. So here are the so it's the top line here. I can't really point at it, but it's in the journal AVS Quantum Science. It's a new journal. I'm actually an associate editor there. So if it's an AIP journal, so it's American Institute of Physics. So it's legit, and so we're looking for submissions. So that's a little advertisement there. But if you want to know more about quantum metrology and this, how we set up this Fisher information and quantum Fisher information, we have a review here. Okay, so. So this is the preliminary part of the talk, and so let me just double check the time that I have. Yeah, so that's so now I will talk about imaging as a metrology problem, and in particular I will talk about the Fisher information of measurement results, of measurement outcomes, and quantum Fisher information of incoming states to talk about the quality of imaging. Hello, yes?
Hello. There's a question from one of my colleagues, Dr. Sabi. So the question is, how is the Fisher information related to quantum entropy?
Yeah, there is a relationship. I can't write, so this makes it a little bit tricky. So later on, I will relate this to the quantum relative entropy, not so much directly mathematically, but when I talk about hypothesis testing. So it's so you may remember from thermodynamics that when you talk about an additivity, and so you want additivity in for your entropy. And you want it to be positive definite, and you there's another one that I forget at the moment. So basically, that says that the only possible state dependent functional for the entropy is the one that we know, rho log rho, right? Where rho is the quantum state of the system. So the Fisher information is like an entropy, but instead of the requirement that it depends only on the state, here it also depends on the derivative of the state. So actually, you can think of the Fisher information as a kind of entropy. It's really an information, right? But there are really close links between the quantum relative entropy and the quantum Fisher information, as well as the relative entropy and the classical Fisher information. And I think I'm going to be cheeky, and I'm going to say, for the details, please have a look at this, because you will have all the we discussed that in here. Yeah. Sorry, I can't be more. If I had a blackboard, I could write it down. But the detail is in the.
It's more or less answered.
Yeah,
it's more or less answered.
Thank you. Yeah.
Okay, thanks. Yeah, it's clear. Yeah, thank you.
Okay, great. So, but yeah, it's a great question. So what I would like to do now is focus on something quite specific, because when we talk about quantum imaging, what do we want to talk about? So one thing you can do is you can say, okay, we want to image something, and we're going to really mess with the properties of what we want to image. So we can maybe sculpt some quantum light, or so for example, in the super resolution work that from the 90s, that started in the 90s, and that is now under very active development. What people do is they do all kinds of masking. They put dimers, on, and then they measure things. They image things by using all sorts of interesting tricks. We wanted to look very much like at distant sources where you can't play around with the source, because that's interesting from an astronomical point of view. It's also interesting from a defense point of view. And you can sometimes you can illuminate something and get some scattered light back. We're just looking at light that comes in, and we have no control. And usually it's going to be thermal light. So we wanted to know what is the best way that you can measure and therefore image distant black bodies. Right? So this is work that was done with my first PhD student and then postdoc Mark Pearce and my colleague Earl Campbell. And so here's the situation. Let's suppose that we have a black body, and we're some pretty far distance r away, so that we can use the paraxial approximation. And then we have two single spatial mode detectors. So basically two detectors, and they're measuring just single frequency modes, single spatial modes. And how well can we estimate, for example, the size, the radius of that black body? Well, so we capture the light in this detector, and so I turned this into a little volume, because we open our detector for a certain amount of time. So you can think of it as like a little drum. We capture a little volume of light, and we want to know in the state of light in that volume, like what is the amount of information about the spatial distribution of your black body source. Right? And so we have a state, so we can calculate the quantum Fisher information. It's not that easy, but it can be done. And so why do we want to do it that way? Well, there is a theorem called the van Sittert-Zernike theorem, and it relates the coherence between 2 points in the imaging plane to the intensity in the source plane. So in gray here we see the source plane, and then we have P at R1 and P at R2 are 2 points in the imaging plane. And then we have a quantity called the complex degree of coherence, gamma here, which if you're familiar with quantum optics, this probably looks familiar. But the most important thing is that you have to do measurements at P at R1 and P at R2. And then when you make these measurements, theoretically, we know that it is related to the intensity. In fact, it's the Fourier transform of the intensity profile in the source. And so when you take many, many points, and you have the pairs of points, and you work out what is the coherence between all pairs of points, then you can reverse the Fourier transform, and you can calculate an image based on the data that you've taken in your imaging plane. So it's very computational, but it is also now a metrology problem, because we need to find an optimal way to measure the complex degree of coherence. However, it is actually a relatively straightforward problem when you think of it in terms of two single modes. Because then you just have the two single modes coming in on the left here. We have some kind of phase that we have to phase shift that we have to choose. Then we send it through a beam splitter, and then we do a measurement. So the beam splitter transmission coefficient is also up for optimization here. And with this, you can basically get any possible measurement of these two modes, linear measurements. And so now, what should we choose for this phase setting? And it turns out it's actually equal to the phase that we want to estimate. right? Because we're doing phase measurements, and so now we're right back to where we started, right? And so so that doesn't work. So so we need some kind of adaptive setup that maybe, you know, we pick something and does this look right, and then increase the precision by slowly tuning phi to the right value. But actually, what we found was something a little bit more forgiving, because you can also grab a whole bunch of random phases, and then what we get is let's see, yeah, here we go. So so if so on the vertical axis here, we see that the ratio of the Fisher information, so what we actually get from our measurements, to the quantum Fisher information, which Mark calculated, which was not easy, but you can see that the ratio stays to 1 for a very long time. And A here is the complex degree of coherence. So if we start to get, when A equals 1, then we have perfect correlation. Right. So and so for actual measurements, you're almost never very close to 1. So you see that because it's the blue line stays at 1 for so long, for a very long time, we end up with a measurement precision that is very, very close to the best that you can possibly do. Right? Because if it's 1, that means that the information that you get out of your measurement is in fact the maximum amount of information that is in the state, the quantum state of the light. So this is very promising, and so this was work done leading up to 2017, and then so much later, I was talking to Andrew White from Australia, and was telling about this result, and he said, "Oh yeah, we have these beautiful detectors. We can probably do this." So they got to work, and they worked really, really hard, because it's actually not so easy an experiment. Lewis Howard was the person who was really pushing this, and many other collaborators. And this is what they did. So they had a laser, and they used spinning ground glass. So the glass was basically made opaque, not quite opaque, but so you lose all coherence, and then you spin it, and then you effectively create thermal light with a very high photon count. And then it's focused on this glass, so you get a little dot. And what we wanted to know is what is the size of the dot. And so we set up the interferometer. The phase was applied by like rotating a piece of glass in the beam going to R1, and then there was a beam splitter, a fiber-based beam splitter, and then we used transition edge detectors because they have a fantastic photon counting capability. And the results were actually pretty astonishing. I mean, I knew it was good because we did the calculation, but when you see an experiment, and I'm not taking any credit here because it's the hard work of the experimentalists, but so we compared two things here. So the important thing here are the error bars, because that's what we're trying to reduce. And so the blue, the count scheme, what we called in the paper, is basically the optimal or close to optimal scheme. And then the traditional scheme is where we basically just pick a fixed phase in the interferometer, because it looks the most like direct imaging. And you see, when you pick a fixed phase, you first of all, you create also systematic error. Sorry, I lost the word there for a moment. But also you see that the blue error bars are really dramatically shorter than the red arrow bars, pink arrow bars. So it really does work. This is now they had to work very hard because the distance between the two collectors had to be fixed within a quarter wavelength of the light. So it's not. This is challenging. And then because we did have an actual experimental error for our method, we could then use that and do like a convolution type demonstration with so this is not real data, this is a simulation where we took a picture of Dory and essentially did the so this is the original sort of the upper left is, and then we go clockwise. So upper left is the 26 by 26 no, sorry, 100 by 100 pixels, but then there is a pixel array, 26 by 26 pixels. And so the noiseless reproduction is given by the top right. Then the bottom right is when we do the regular imaging, and you see the contrast is quite low. And then when we use our method, we get the bottom left, and you see that it is the same resolution. We don't see more detail, but we reduce the noise by a lot. So there's less noise. So this is really the big improvement for measuring the complex degree of coherence. So you get a less noisy signal. So I like this picture because I just stole it from the internet, but I put my own labels on there because I can imagine, in terms of a technology sense, that we can have a CCD camera, and we can have a lens that gives us the basically the beam that plays the role of the beam splitter, and then we have an SLM, right, which basically gives us random phases. And then we can just take data and calculate, and it's going to be a lot of data. We calculate all the complex degrees of coherence, and this way, I predict that we should be able to make much less noisy images. So that's one route to technology. And then, so that's basically lowering the noise, but we kind of also want to get a better resolution. And one way to get a better resolution is to extend the baseline. So that's another topic. So traditionally, when we talk about resolving power, it's a very operational definition. Typically something like, what is the minimum resolvable distance between two dots or slits? So if we look at the image on the left here, it is in the image plane, we have two dots create point spread functions that when the two dots get too close together, they basically become one dot. Right, and so there's a limit to how close the two can get before you can no longer see that there is in fact two of them. And same thing with slits, you can define it that way too. And so this was done a long time ago by Ernst Abbe. So he worked with Carl Zeiss. So he basically was very much. It was about creating better optics, and so he came up with this famous in optics circles formula. That's basically the distance that you can resolve is the wavelength divided by 2 times the index of refraction times the opening angle of your aperture. Right, so your lens opening. Okay, so now recently, 2016, there was a big shockwave through the community because Mankai Tsang and his co-workers demonstrated that actually you can get rid of this. He called it the Rayleigh curse. This limitation that you cannot. That basically you cannot distinguish between 2 point sources when they get too close to each other. And so the way that works is, any separation S between the 2 point sources, the 2 stars there, you can see, because for very small s, the state that you get is psi x plus or minus a half s. And so if you do a Taylor expansion of this, we end up with psi plus or minus something that goes with the derivative of psi. And when you take the derivative of a Gaussian, assuming a Gaussian, you get orthonormal functions. And once you have orthonormal functions, you can construct your observable so that you can tell exactly which one of those which one you have. So so that was a big bombshell. Unfortunately, super resolution for in general, I mean, it's true. What Mankai and his co-workers wrote is true. The catch is that this only works properly when the two sources have the exact same intensity, exactly equal in brightness. And so when you have like an unequal brightness, for example, exoplanet detection, it's quite an extreme case where you have a really bright star and then a dim planet, then the fraction is off by quite a bit. So in the top plot here, you see that the fraction Q is a half, that means equally bright. And you see indeed that the maximum position is just like one straight line all the way down to 0, because on the horizontal axis is the distance between the two. Here it's D because it took it from a paper, and I called it S in the previous slide. And then in the yellow dotted line is the precision of direct imaging. Right? So actually, when you change the relative intensity of the two sources, it no longer stays finite when you get to 0 distance. It actually drops to 0. But interestingly, it still stays quite a bit higher than the maximum precision that you get from direct imaging. Right? So in that sense, we can still call this super resolution. And I think the community has landed on that we call this super resolution. So then we did some theoretical work with Cosmo Lupo and Xijing Wang about, okay, what can you achieve with linear interferometry? Because as you remember, the experiments that I demonstrated and the theory that I demonstrated earlier was all linear interferometry, beam splitters, phase shifters. And so we set up the following. What if we have n weak incoherent emitters, so a star cluster or whatever, somewhere far away in a three-dimensional volume, and we want to measure something where we have m light collection positions in this collection plane, and then we send it all into an arbitrary m mode interferometer that we indicate by R, and then we do photon counting. So we have complete control over the interferometer, but we have no control over the sources. And what we found was that we can create like a generalized parameter that is some combination of the 3n coordinates, right? So every source has 3 positions, x, y, and z. So we've got 3n coordinates. We can, for example, look at the what's the center of mass of these sources. What is the most the outlier? Also, anything that you can come up with that is some combination of these coordinates. We can actually image. We can calculate the quantum Fisher information for that particular parameter. We can also construct an interferometer that gives rise to a classical Fisher information. And what we showed is that we can get an R that gives a classical Fisher information that is equal to the quantum Fisher information that we calculated from the source itself. And that means that we found the optimal measurement. Right? So, when we did so with linear optics, which is really quite cool. So there is no need to do any nonlinear processing of the light. So that's quite powerful. So the conclusions that we get is that we can optimally measure the spatial property of a set of light sources. So we did not actually put any restrictions other than that were in the paraxial regime on the sources. So they don't have to be, well, okay, there are point sources, but you can imagine that you can get more continuous sources as well being built up from this. And it can be achieved optimally using linear optical interferometry. And it beats the Abbe limit. and it's therefore a super resolution technique. So, so that's really exciting. And so we are talking to experimentalists in order to try to figure out, can we do this in astronomy, right? Which is a very obvious application. Now, doing a single parameter is still only the first step, because yeah, maybe that's not what you call imaging, but nonetheless, it is an important first step. The problem that you have with multiple parameters is that for each parameter you may need a different R, and maybe you can set only use only one unitary R at a time. And so if we have non-commuting measurement observables, then we get into trouble a little bit. And I've skimmed over that for the complex degree of coherence, but it's already happening there as well. Okay, so so then looking at this,
there's a question. Hello.
Yes.
Hi.
Yes.
Yeah. Or maybe you can directly.
So I have a very simple question about this technique. So we are gaining in resolution. So the measurement is optimal vis-a-vis resolution. But are we compromising on the brightness or the intensity that we can get in the image plane?
Not really. So the idea is that you capture everything that you can. Yeah. So so I will actually mention this again, especially now that you asked me this, because it's a very good question. Because you may want to do something like correlation measurements, in which case you need multiple photons from a source. And if that's the case, maybe you're throwing a whole lot of data away, right? And so I will, in fact, I'm going to answer the question. That's the very next thing. So so thank you for that. That's so in this case, no, we're not throwing any data away. We're using everything. And so we're not paying a price in terms of so we chose weak incoherent sources because with bright sources everything is easier. It's really weak makes it mathematically more simple, but also it's the regime where you're most interested in. Yeah. Okay, so yeah, so exactly this problem we analyzed with a group in Erlangen, Joachim from Zantier and his group, and so we looked at the difference between intensity interferometry and amplitude interferometry. Okay, so what's the difference? So in the 1950s, Henry Brown and Twiss did measurements of Sirius and other stars, nearby stars, and they wanted to know what is the diameter of the star. And we don't have telescopes that are big enough to see the actual, to resolve the actual star. Betelgeuse, yes, we can actually see the actual image with direct imaging now, but I think Sirius is still not, is still too small. So what you can do is you can do intensity interferometry, and then you don't rely on interfering the collected light. So in the previous example, we had the light, it was collected, and then it went through a beam splitter, and so we needed a coherence all the way through the system. And in this case, we're just measuring, well, I say we're, Hembury Brown and Twiss did this way back, and I've never been anywhere near a setup like this. But my colleagues in Erlangen, they do. You basically, you just measure the photons here, measure the photons there, and then you correlate the intensity that you get. Right, so that makes it much easier in terms of not having to worry about, you know, that's the two collectors are like perfectly within a quarter of the wavelength, and that sort of thing. So because you can have quite a big imprecision in the position of your detectors. Right, but you pay a price because you also have the situation that this requires that you get two photons from a thermal mode, and thermal modes have on average very few photons in them. So the pros is that we can get really, really large baselines, and the bigger the baseline, the better the resolution, because the baseline basically determines your numerical aperture. So that was the sine alpha in the denominator of Ernst Abbe's formula. The con is that we want photon coincidences, which are very rare. And so this is an example of exactly your point, the person who asked the question, where yes, we all the times we have a single photon that actually carries information about the spatial distribution, but the intensity interferometry does not have access to that. So then the question becomes, right, so we can only get so far with interferometric imaging, so where we have what we did before, where you send your light through a beam splitter, because if you go too far, you start to lose coherence. And there are practical limits, not so much fundamental limits, but practical limits. And so we looked at, I think it was on the order of 50 meters, and then we looked at the intensity interferometer, and we put that much further apart, where we're basically pushing up against the limits of what's practically doable. And so then we calculated the quantum Fisher information and see what does it best. And so this is the situation. Again, we are looking at these values for Q for these 4 plots in the top left corner. So 0.5 would again be equal brightness, but we kind of don't want to look at that because that's the one where everything is flat. And then so we have a bunch of actual telescope arrays. So there's the ELT. So there's 2 plots for that's the extremely large telescope, I believe. There's also a telescope array that's called Chara, and then there's the very large telescope. That's the yellow one. And so we used the characteristics of those telescopes, the baseline, the size of the mirrors, etc. And then we compared that with an array of detectors that can be put much further away. And but again, you pay the price in terms of lower photon output. And so you see that the blue line, the intensity interferometry, when and on the horizontal line, I should say, this is the distance between 2 sources, right? So when the distance is large, then you see it always does worse than any of these amplitude interferometry telescopes. But when they get really, really close, then the intensity interferometry can enters a regime where it is actually better than the imaging from these amplitude interferometry arrays. So there is definitely room for looking at very specific. So these are very specific use cases. But also, it is you don't need very large telescopes to make this G2 array. Right? So you need big collectors, but you can put them on. In fact, they put them on a tractor, and we're driving around the field. And this is not experimental data, but they're working with that. So it's very practical in a sense, and in certain cases has a clear benefit. All right, so and then finally, this is a paper that appeared on the archive a week ago, and it is a paper by the group in Harriet Watt. Ugo Sanvolin was the lead experimentalist, and Zijin was the designer of the experiment, and it's somewhat similar to the first experiment that I showed, but here we're looking at hypothesis testing. And so I mentioned in the response to the first question, what about how is the Fisher information related to the relative entropy? So here we are actually looking at the relative entropy, because we have 2 hypotheses. Hypothesis 0 is there is one source, and hypothesis 1 there is a second source with a brightness, so the brightness is like split with a 1 minus epsilon and an epsilon. And an epsilon typically here is small, Right? So the obvious application, of course, here is exoplanet detection. And so what we want to do is we want to collect all the light, and then we want to do some kind of measurement in order to be able to tell the difference between the two. And so here's the experimental setup. And so there is a laser that is being phase modulated and amplitude modulated. So in the previous experiment, they used a ground glass disc that was spinning to create incoherent light. Here we have incoherent phase and amplitude modulation. And so then it goes through a mask. There are some neutral density filters that can be placed on one opening. So there's like 2 openings in the mask, and so we can put different epsilons in there. And then we have 2 collectors, the 2 points there with where the blue lines come out, and so these are fibers. And there is going to be a feedback control loop that essentially allows this thing to stay interferometrically stable. So this is one of those, experimental wizardry tricks that's really nice. It's, Ugo has a very nice setup here. And then we're basically doing measurements and trying to and working out. So we're working out what is the best possible measurement, and then we want to know what is the best. So what is the relative entropy for these 2 hypotheses, and we can have a look at the precision as well.
Yeah. There's a question, Peter. Yeah.
Yes.
It's in the chat box. So yeah.
Maybe I can.
Yeah.
So let's. Yeah, my mouse doesn't show up.
Okay, for this to work, how did your group assess to the density matrix? I want to know about quantum state tomography for such a large system in terms of dimensionality of density matrix. After all, there would be thousands of photons involved, and how did you apply measurement optimization, since optimization is a NP-hard problem?
Yeah. So now I have to. Okay, so so it's not NP hard, and the reason for that is that it really goes into the details of how you calculate the quantum Fisher information and how you calculate the classical Fisher information that comes out of the interferometer, and so it's trying to figure out the best way to phrase this. So yeah, it's difficult to explain without having the maths present. But so we did this for any n, right? So it's an analytic result, and what we actually end up with is a matrix R that describes our interferometer, where every matrix element is precisely defined by the quantity, the parameter that we want to estimate, and the parameter that we want to estimate that was given by all the locations and the weightings between them, right? So it's a constructive proof in the paper, and then after that you have a matrix, and so now you have to translate this into an interferometer. And this is where we use an old result by Reck and Zeilinger from 1994, where they give a recipe for any matrix that you have. You can decompose into phase shifters and beam splitters. Now, you still probably want to optimize how you do that, but and that may be a difficult problem for very, very large. So it's. Oh, and the other thing is we're talking about the sources here, right? Not the photons. So the photon, because we're using thermal light, each photon does its own thing, right? Going through the interferometer. That may be actually the real answer to your question. I may have read it wrong. Okay, so Yeah, so they can't see my mouse, so I can't click away my text. You do not see my chat box, do you?
No, we don't.
Okay, good. So I'll just go around this. So, so we want the relative entropy of the two hypotheses to be as large as possible, because that tells us that we can really distinguish between those two hypotheses. Being, is there a second source there or not? That those are the two hypotheses. And so if we compare this here with direct imaging. So the blue line is the quantum relative entropy for when we have two modes, and the dotted yellow line is the classical relative entropy for this particular setup with a visibility of 99.5%. So because the visibility is something that you try to get as good as close to 100% as possible, but once you know your visibility is low, you already know how that is going to affect your relative entropy. So so that's like a modified classical relative entropy, and you see that the experimental data lies beautifully on top of the classical relative entropy there. So this system is extremely clean, and then the other thing to note is the scale on the vertical axis, right? So the tick marks here go between factors of 100. So we really do have 2 orders of magnitude improvement with this system. So it's and I when I first saw this data, I was blown away. And then if you look at the horizontal scale, you see that epsilon is really tiny, right? Maybe not quite tiny enough for well, actually, it seems to continue. So maybe exoplanet detection will work here very well as well. And then the other thing we did was look at the mean square error, and we normalized things here so that the quantum Fisher information is now given by the blue horizontal line at the bottom, and then we compare that to direct imaging if you were just to use a lens, and that would be the green line, the top one. And you see that the mean square error is much worse. And again, the yellow band here takes into account the visibility of the actual experiment, which we of course have experimentally as well. And again, the experimental data lies really close to the optimum. So for all practical purposes, we can say that we've done an optimal measurement of the distance, or actually it's the opening angle that is being measured here, the opening angle between the two sources, right? So it's incredibly precise, and so it requires a fair bit of advanced kit in the lab, but yeah, it's very feasible. I see a question, so I'm just going to answer it if you,
sure,
because the chat box is open. How can we get visibility up to 1, since we need exact number of photons for maximum intensity and of course for minimum intensity? No, so the visibility is something that you get. So you don't require any. This is a purely experimental quantity. So how do we get it up to 1? Well, with a lot of hard work. The Heisenberg limit just is not involved here, right? So because even if you have, I see what you mean. So even if you have a perfect visibility, it's not the 1/n Heisenberg limit that squeezes this. It's the slope that determines the Heisenberg limit. You always have a certain slope. You can't make the slope infinitely, like that. That's where the Heisenberg limit comes in. Yeah. Okay, and then so I have some conclusions. So basically, and I can't read what I wrote here, but we can extract. Yeah. So the point is that by looking at imaging as a fundamental quantum metrology problem, we could design optimal imaging machines, devices. right? And then and we can this allows us to reduce the noise in an image and also improve the resolution in an image, right? So we can go beyond the Abbe limit of resolution, and this is all for classical incoming light. So we've not done any tricks to modify the incoming light, which is important for astronomy and potentially, sadly, military applications. And also, I think what's and this is really for my experimental colleagues to really take a bow here. It demonstrates that this is completely feasible. The results are quite remarkable, and yeah. So I hope that you enjoyed this little tour of the work that I've been doing with many talented people, and yeah. So with that, I would like to thank you very much for your attention, and any questions I'm happy to answer.
Yeah, thank you. Yeah. Guys, yeah, great talk, Peter. So, any questions?
Thank you.
Yeah. G, okay, yes.
Am I audible?
Yeah, I can hear you. Yes.
Yeah. Thank you, Professor. It was a really amazing talk. My name is Abdullah. So my question is that the function which allows you to calculate the coherence between the imaging the data sample and from to the points of the source. So my question is that does that function incorporates all of the parameters or one parameter at a time? And if if it incorporates multiple parameters, so and if the parameters do not commute, which you mentioned somewhere in your presentation, so experimentally we only have a choice to measure one parameter at a time, and if the parameters do not commute, so is there a way to figure out the optimal parameter which we need to consider?
Yeah, thank you. That's an excellent question. So, you were thinking of the faceted Seneca. So let me just do a quick share screen so that you can see what we're talking about. So you can see my screen now, I believe.
Yes.
Yeah. So so this is the if you can see my mouse, so I'm pointing at the gamma here. So this is the complex degree of coherence, and so because this is the entire distribution, so the entire image source, not image source, right? The gamma at 2 points is basically a convolution, and it has information from everywhere in the source plane. And so now what we need to do, so what you're saying, like, yeah, you just do measurements and you get this this number here, but that's just one number, and you're absolutely right. So what you need to do is you need to set up a system where you have many detectors in your entire image plane, and then you want to correlate, so you calculate the complex degree of coherence from your data at between every pair. Now there is some issues here that gamma is a complex number, and there's some trade-off here where you cannot measure both the phase and the magnitude of gamma simultaneously. So you're gonna need to take double the measurements if you want to. So that's just no way around it. But in principle, you can fill the entire image plane with detectors, and then do post-processing like so, where we have the image plane is filled with detectors. We've got our beam splitter, which is now a lens, and we've got our phase shifts, and so you can basically calculate the complex degree of coherence from the experimental data, and then you take those this big matrix for the complex degree of coherence, and you can take the Fourier transform of it, and then you can reconstruct this IS, because now the Fourier transform runs, in the opposite direction, right? So you integrate the gammas, which is now a sum because of the finite number of detectors. Does that answer your question?
Yes, sir. And I have like a follow-up question, and that is there a possibility of quantum coherence between two data samples or two photons coming from the same source, so that that appears as noise, or that appears as a coherence with the environment, but that actually is the coherence between two different photons from the sample. So we aren't taking that into account in the mathematical calculations. So is there a possibility of that?
Yes. So let me just. So I know exactly what you mean, and the answer is absolutely yes. The thing is, so if I look at, let's say, something comes from the origin here, so I treat this as the source. Now, if this is an incoherent source, that means that we have thermal light coming from it, and for most thermal light, if it's like from a star or something like that, or reflected light, starlight reflected by a planet, what we end up with is many modes. There are many optical modes, right? Different frequencies, but also different K vectors, and so when you look at a single mode, right? Because there's lots of photons coming from starlight, but because there's so many optical modes, all those many photons are actually spread over even more optical modes. And so every single mode has very few photons in them, which is exactly the problem that the Hanbury-Brown twist experiment has. Namely that you have like maybe, so there's a quantity, like the probability that you get more than one photon is like 1 in 1,000. Right, so actually it is, so it's quite, so it's quite rare that you have to deal with this. And so now this we used, I'm just trying to remember, because this was before 2017, how we did this, and I think this is a purely classical expression for the complex degree of coherence, so for the classical Fisher information. But then in order to compare this to the quantum Fisher information, we had to calculate the quantum Fisher information for the light in there. And if I remember correctly, we did actually take into account the full thermal quantum state. So the multi-photon contribution would be included. So I'm 95% sure that that's how we did it, because I remember Mark, Pierce, and I, we talked about this for over an extended period of time, because it was a very difficult problem to solve. Yeah.
Thank you, sir. Thank you for your time.
Thank you.
Hi, Peter. Am I audible?
Hi.
Oh. So my name is Bilal, and first of all, thanks for such a wonderful talk. It was amazing. My question is,
thank you.
My question is from the second last slide where you had a graph. Can you please go there?
Yeah. Is it this one?
The one above it.
This one.
Yeah. So here you have your experimental data, and the green graph, the one you have for direct imaging. Is it for a system where you are using a simple lens to capture the image? So have you tried comparing your results against an optical system that uses mirrors to cancel all the aberrations? Because I think that's a better benchmark for the modern day optical systems to compare your results against.
Okay, so when I say we use direct imaging, we use a lens. We use a lens with no aberration, and so effectively, I think, because that's mathematically a lot simpler. And so effectively, yes, you're right. A system with mirrors works much better in that regard. And so I think here you can read that as using mirrors for all practical purposes.
Oh, all right.
Yeah.
Thanks.
Yeah. Okay.
Any more questions?
I have a question, please, sir.
Yes. Yeah. Go ahead.
Yeah, I am very much basically, thank you for the nice talk. So I am very much interested in understanding the what if there is any explicit connection between the Fisher information with entanglement as well or not, because
yes,
yeah, people have been working on quantum Fisher information in Heisenberg spin chains. So I have been following the papers. So I am interested in the connection between entanglement, coherence, and Fisher information.
yes.
Because I was studying a paper in which they have basically said that Fisher information can be used as a faithful resource quantifier in any quantum system. But since as I'm a student right now, so I wasn't able to understand whatever was the goal of the paper.
Right. Yeah. So no, absolutely. So in order to meet the Heisenberg limit, you need entanglement, and you can see that there is entanglement here because it's the entanglement between the two modes. Right? It's a bit funny if you think of n equals 1, then you have a single photon, and how can a single photon be entangled? But really, the entanglement is between the optical modes, because entanglement is not between systems, but between degrees of freedom. And so if we think of the number of photons in a mode as a degree of freedom, then you can see that we have an entangled state here. And in order, so this is the classical situation. And you see that the Fisher information here is 1, and we repeat it n times, and we get our 1 over root n. And so when we do this with entangled light, then we can push this up to 1 over n. Now, this is super complicated to actually achieve, and it has all sorts of drawbacks that you probably don't even want to. But from a theoretical point of view, it is a really nice illustration. So you need entanglement. You need to entangle your resources that you use to probe your system in order to get the full benefit. So the paper that the paper that proves this, that first saw this, is by Giovanetti, Lloyd, and Marconi from PRL in 2006. I'm just going to be cheeky, and I'm going to put this one up again because it's in there as well. Yeah, we talk about entanglement and point to some relevant literature. And if you have any questions, feel free to also drop me an email, especially if it's specific questions.
All right, so just kindly share your presentation in the chat box if possible, sir. That would be great.
Yes.
Yeah.
Yes. I'll have to figure out how to do that. I think what I'll do is I will coordinate this with Atta, so that because I will have to go at 3 o'clock to pick up my daughter from school. And so I will send a PDF. Yeah.
Okay. So I think to give you the benefit of some time for that thing. So we would like to thank you again, Pieter, for such a wonderful talk. And
thank you. I mean, I still have a couple of minutes, so there's no rush.
If there are other questions from the audience, anyway, so I can share the email, and then if they have questions, they can write